Okay, Landon, what do you got? Were you able to find it? I'm so. Oh, all right. What? Yep. Okay. Okay. Do you remember what problem number it was in the homework? Okay. All right. So using the law of logs. Nope, not Allen one. Okay. So not a 10 to the 1, but you're close. Okay, so the natural log is just another way of writing log base E. Log base 10 is the common log. ln is a log base E. It's an ln. So that means if I use the definition, e to the first power has to equal x minus 5, x plus 6. No, e to the first is just e. Do you remember how much e is? Yep. Yep. So I guess my question to you at this point is what were the full instructions for this particular problem in number 10? Okay. Just solve for x. Did it say to use a graphing? All right, hold on. I need to check something. Do you have the thank you. Oh, number 66. Yeah. See, I don't like that. I mean, we can. I don't know if I like that though. Kaylin, do you remember this one? Remember what you did? I'm just curious. This bit. No. You don't have to do log of e. From here, the other route is to think of it as e to the ln x minus 5, x plus 6 equals e to the 1. Then these two would cancel out. And you'd have x minus 5, sorry, x plus 6 is equal to e. So then what happens is you end up with x squared plus x minus 30 minus e is equal to 0. So the only thing we can do at this point to solve for x is to use a quadratic formula. -1 plus or minus the square root of b squared minus 4 times 1 times a -30 minus e. And this is just a weird square root, so yeah, you can do it this way. But the weird part about this particular method is that all of this is your c, right? A, B. So all of this -30 minus e is your c value. I'm sorry, Landon? I'm just using the I'm just using the quadratic formula. X squared, all I did was FOIL this, right? X squared minus 5x plus 6x, that's a 1x, minus 5 times 6 is a -30. And then so I could use the quadratic, I had to subtract e from both sides. So I've got an x squared plus x minus 30 minus e. The weird part about this is that e is just that 2.718. It's just a stand-in for that number, right? So that makes all of this my constant or c value in the quadratic equation. Yep. Minus 4 times a times c. So I've got a -1 plus the square root of 121 plus 4e. Divide that by 2. Or a -1 minus the square root of 121 plus 4e. Divided by 2. I bet that's a 2. I'm just plugging it into the calculator. So -1 just one at a time. -1 plus square root of 121 plus 4 e to the first, because it's just e. Close those parentheses, because that's my entire numerator. And then I have to divide that by 2. And then I did a -1 minus square root 121 plus 4 e to the first. And again, I still need to divide it by 2. So a -6.242. Were there others? How did the applications go? Oh, okay. Sorry. Did I get that right? Does that one say to solve graphically? Or use a graphing device? Okay. I'm just pulling up Desmos here, just so you know what I'm doing. Yeah. Okay. Yeah, this is. Okay. All right. I just would like to point out that the first thing that you should do here is to solve this for 0. So I'm going to rewrite this as f of x is equal to x squared minus 1 minus the log of x. Yeah, so then that's what I plugged into Desmos. Hold on, let me. Okay. Yeah, I know. So then when I look at this, I've got a solution. Let me zoom in. There you go. So now you can see what our x values are. We've got a 1, 0 and a 0.1020. Okay. Yeah, that's what should work. If it doesn't work, send me the link to the question again. Use that ask your instructor thing, and I'll do a little bit of a deeper dive into it. Okay. Oh, okay. Okay, great. Great, great. Okay. Any attempts on the application or word problem ones? Oh, the atmospheric pressure one? Okay. Is it blinking on you? The fish population? Okay, small lake is stocked with certain fish. The fish population is modeled by the function. The population is equal to 10 divided by 1 plus 4e to the negative 0.8 t. Is it blinking on you? Okay. All right, it's flashing on me like it's going to give somebody epilepsy. Somebody with epilepsy is not going to have a good time with this. Okay, it's not doing it for you guys. Great. All right, what's the question? Where P is the number of fish in thousands. Yeah. Because it's just plugging it into a calculator. Yeah, with a 5 there where the T is. Okay, do you have the same calculator I do here? Okay. So what you want to make sure that you're doing with your numbers is in your denominator, you want to make sure you're putting all of this in parentheses. And in addition, that you're putting either figuring out what this number is or putting it in parentheses as well. So if you're doing it all in one fell swoop, you want to make sure to put the denominator in parentheses as a whole, and then whatever your power is, either calculate that number out first, and then you won't need parentheses. Or if you're not going to calculate it out and do like 0.0 whatever times 5, then you want to make sure you put that calculation in parentheses. Okay, so your number here was a 12. So this was a 5. Oh, yeah, it was a negative 0.08 times 5, right? No, that's not going to work. 4. There we go. Sorry, I just had to think that through a little bit. Okay, so when I type that in, I'm going to do 12 divided by parentheses 1 plus 4 e to the, sorry for the glare, 2 or 0.0, whoops, it's a negative. Negative 0.4 times 5. And then I'm going to do another set of parentheses again. So what did you have to round to? Oh, this is your fish population, right? 7.7854 to the nearest fish. Remember, you got to multiply that by 1,000. This is your fish population in thousands. It's not saying there's just 7.78 fish. It's saying there's 7.785 thousand fish, or 7,785. No, there's not going to be 8,000. That's if you round to the nearest thousand. Yes. Why not? We do this all the time. I mean, our population, we say it's 38.5 billion. And if it's 38.5 billion, that doesn't mean there's just 38.5 people. It means we have to multiply that by a billion. They're saying this is 7.7854 thousand. So we've got to multiply by 1,000. Yeah. We won't do 6,000 again because this formula uses P in the thousands. So rather than using 6,000, there you go. You're just going to use 6. Yes. Yes. Yep, then you've got to solve it for T, just like we've practiced. Multiply both sides by your denominator to get it out of the denominator. So you'll have 6 is equal to 12 over 1 plus 4 to the e negative 0.4t. So I'm just going to multiply both sides by 1 plus 4e to the negative 0.4t. And that eliminates the denominator. Then I would go ahead and distribute so that you can begin to move terms around. 6 is equal, whoops, not equals. 6 plus 24 e to the negative 0.4t is equal to 12. And I'm going to move the 6 over. Sorry? Okay. Yeah. Whenever you have a denominator, you just want to multiply by the lowest common denominator in order to get stuff out. I have ln 1/4 or ln 1 minus ln 4. Yeah. Okay. Now you want to divide both sides by the 24. And once you have just the e, sorry, oh, don't spill water on your electrics, Amy. Okay. Yep. Now you can take the natural log of both sides and go from there. Okay. Good deal. All right. So I'm going to go ahead and move into 4.6, which is just more modeling with exponential functions. Okay. Exponential growth, doubling time. So there are a few sort of basic formulas that we use on a rather significant basis for modeling many different types of growth. The first one that we're going to talk about is modeling time to double. So how long does it take something to double? This is an exponential growth formula. The formula is n of t is equal to n of 0 times 2 to the t over a. Hold on one second, please. There's someone knocking on my door. In the tub. Hi. Oh, can you just put it in the plastic tub there? Great, thank you. You too. Okay, sorry about that. Sometimes people don't read instructions. All right, so this occurs where n sub 0 is the initial population. A is your doubling time. And T is the current population. All right. Now, it should be of note that the doubling time can be any measure of time. So your doubling time could be 2 weeks, 2 days, 2 months, 2 years. Your current population should be in the same units as A. So we're not measuring one in weeks and one in days. That just should not happen at all. Now, our exponential growth known as the relative growth rate, is n of t is equal to n sub 0 e of rt. Where n sub 0 is again our initial size. R is our relative rate of growth. And t is again our time. Okay, so some sample problems here. Oops, wrong way. I wanted to go up. Here we go. Bacteria culture has 25 spores and is known to double every 5 hours. All right, find the exponential model for the number of spores after T hours estimate the number of bacteria after 18 hours. And then we're going to use that formula to calculate or determine how long it takes to reach 1 million spores. Okay. With this exponential growth problem, we have the chance to use one of two formulas, the two that we just talked about. The first is used specifically when we're talking about time to double, and the second is used if we're looking for a relative growth rate. So, based on this initial problem, a bacteria culture has 25 spores and is known to double every 5 hours. I'm going to go ahead and set out to use this formula because this formula is used specifically with doubling time. So I'm going to have n of t is equal to n sub 0, which should be our initial population. And for this problem, our initial population was 25 spores times 2 to the t, which I do not know, over a, or the doubling time, in this case, 5 hours. This is my formula. N of t is equal to 25 times 2, and people will write it t over 5. People will also write this 25 times 2 to the 1/5 t. People will also write this 25 times 2 to the 0.2 t. All of these are the same formula. Questions? Landon? All right. Okay. All right. Part B asks us to estimate the number of bacteria after 18 hours. This says we're going to let T equal 18. So now instead of N of T, this is going to be N of 18, or 25 times 2 to the 18 over 5. That means I need my calculator, and I'm going to type in 25 times 2, and in my exponent, I'm going to do parentheses 18 divided by 5. To get 303.14, or about 303 bacteria. All I'm doing is putting in the numbers I'm given. Part C asks us to determine how long it takes to reach 1,000,000 spores. This says that N of T is 1,000,000. 1,000,000 is our results. That's going to be 25 times 2 to the T over 5. I can divide both sides by 25. When I do that, I have 40,000 is 2 over T to the 5th. I need to bring that exponent down. So to do so, I can either use the natural log or the log base 10. I want one I can use in my calculator. I'm just going to use the natural log because I'm lazy and it's one less letter. This allows me to bring my T over 5 down. Now from here, I can do a couple of things. I can multiply both sides by 5, but I will also need to divide both sides by ln2. So my T will equal 5 times ln 40,000 divided by ln2. To figure this out, I need my calculator, and I will type in 5 times ln 40,000, figure out what that number is, and divide it by the natural log of 2. And I'll get 76.4, keeping in mind these are hours. So it'll take just a little over 3 days. Just a little bit over 3 days to reach 1,000,000 spores. Questions? Okay. All right. Great. Well, let's see if we can get at least get a second example in here. All right. All right, so species of bird was introduced 25 years ago. It has a relative growth rate of 12%. The original population was estimated at 24, or at 54. Let's try 50. Yes. Um, for the most part, my experience has been you don't always recognize relative growth rate. Like it doesn't always say the relative growth rate is, but it almost always says doubles. Like the double one clearly has to say doubles someplace. So that's usually what I look for first. And if it doesn't say double, then I go to the relative. You're welcome. We're going to find a function that models the relative growth rate over, that models the relative growth rate. That's part A. Part B says what's the population in 25 years. And then part C says how long until the population reaches 2,400 birds. Okay, so find a function that models the relative growth rate. Relative growth rate, if you recall, is n of t is equal to n sub 0 e to the rt, where n sub 0 is your original population, r is your relative growth rate, but we will write it as a decimal, so we'll use 0.12t. So our n of t is 54 times e to the 0.12t. The population 25 years later, or in this case, what would be the current population, would be n of 25 is 54 e to the 0.12 times 25. Again, I need my calculator for this. 54 times e, 0.12 times 25. I'm letting this do the calculation, so I'm going to be sure to close that parentheses. And I get 1,085 birds. I get 1084.6, but I'm going to round that up to the nearest whole bird, since I can't have part of a bird. And then the third part asks how long until the population reaches 2400. So this is saying 2400 is 54 e to the 0.12, and we're missing our time. So in order to solve this, I have to divide both sides by 54. Which gives me 400 over 9. Then I'm going to take the natural log of both sides. Oh, you mean because I got a repeating decimal? Yeah, you can do it. You can know your math to do it, or you can use your calculator. So we had what, 2400 divided by 54. I just use my second key and then my fraction to decimal. And my calculator tells me that's 44 4/9, which I can use my second and then hit the fraction button, and it'll switch it to an improper fraction. So this is going to be using the laws of logs, ln 400 minus ln 9 is 0.12t. So I'm going to have ln 400 minus the ln of 9 over 0.2. So I'm going to do the ln 400 minus ln 9 first, because that's my numerator. Figure out what that number is, then divide it by 0.12. To get 31.6 years is approximately my time. All right, this is going to be enough to get you started on 4.6, but I did not get to exponential decay, nor did I get to Newton's law of cooling. So tomorrow's Q&A is going to be a lecture on those two topics. You are welcome to attempt the questions and see how it goes, but I have a feeling you might need to see some examples. So we will take tomorrow's Q&A and make that lecture on those two examples, or examples on those two topics. But that's the last lecture we have for the term, really, for chapter 4 and really for the term. So, right? Anything else I can help either of you with? Okay. Sure. Mm-hmm. Log base 2 of log base 3 of x. And you had it equal to what? Okay, so basically I'm just going to use the definition. And by definition, we know that 2 to the 4th power has to equal whatever the result is here. So 2 to the 4th power has to equal log base 3 of x. Two to the 4th power is 16. And then I can use the definition again and use your base of 3 to the exponent 16 has to equal the result of this log, or x. That's going to be a just wonderful number. No, I don't need, there's no division. I'm not dividing by logs. I'm using the definition. This is my base. This is my exponent. That's the result. So 3 to the 16th power has to equal x. I'm just switching between exponential form and log form. Way back from 4.1. Okay? All right. You're welcome, guys. And if you need anything, Landon, use that Ask My Instructor. I know you need some of it like just in time when you're working on it. But don't be afraid to send me a message and put it aside until I can answer you back. You're probably frustration-wise better off that way. Yeah. Like, I don't get this one, I'm going to send Amy a message, either Snapchat or through WebAssign, and just wait until I can get you back, even if I'm in the middle of something, even if it takes me 15 minutes. Frustration-wise, you might be better than to do that than to try it 4 times and hit that sort of difficult frustration level. Okay, you're welcome, Landon. Caitlin, it was good to sort of see you today. It's okay. It's okay. You're getting your work done and all is well. So no worries. All right. Okay. Thank you guys. Have a good night.